Hi, this is Mr. Champlin. We are looking at Chapter 5 out of the Schnick book, Angular Momentum. So let's get started. Definition of angular momentum. We have two equations here on the left. Angular momentum symbol is L, is equivalent to R cross P, R being radius, P being translational momentum. Another equation for angular momentum for a rigid body is I cross omega. And basically I wrote this here. First equation is used for an object rotating about a point outside the system. So something like this. Here's the point of rotation. The system is rotating outside. R is the distance from the center of rotation. There it is. P is the translational momentum. So I gave an example of satellite around Earth, planet around Sun. This second equation is an object rotating about a point within the system. So here's a rigid body, a sphere it looks like. The system has a rotational inertia I and rotating omega radians per second. Examples, a flywheel rotating at an angular velocity, bike tires spinning on an axis. In order to get the direction though for omega, that's a little tricky. For angular momentum, you have R cross P. So it would go up, and it's always perpendicular to either one of the P or the R. And then the other angular momentum, you just follow the direction. You cup your hand, and you follow your fingers go in the direction of the omega, and your thumb would be going in the direction of the spin. So if I put my hand around that spinning sphere, omega would be my fingers cupped around the sphere, and my thumb going in the direction of the spin. And you can add angular momentum, so you can notice that they add up to a total between the two of them. It's like adding vectors. Conservation of angular momentum. Angular momentum L of an isolated system is conserved. The final angular momentum L sub f is equal to the initial angular momentum. So this cartoon is supposed to show that we have a person standing out on a spinning turntable, and the weights are extended away from his center of rotation. The center of rotation would be right down the middle of him. These weights are extended away from him. As he brings the weights in, he is effectively decreasing his I, because we know from the past that I consists of M and R. Well, obviously his mass hasn't changed. He hasn't dropped any weights. His mass is the same. But his R has decreased because the weights are closer to the axis of rotation. So therefore, to conserve angular momentum, the angular velocity increases and he spins really quickly. And if he would extend these back out, he would slow down, because it would be like this, set up a greater I and a decrease in omega. All right, we have a couple examples. Let me get the pen here. First situation is a satellite. Here is a satellite going around an elliptical orbit. This is a planet. It's just going to orbit right around here. It says that the satellite speed at point A is 8,000. So right here it's 8,000 meters per second. What is the angular momentum at point A if the satellite has a mass of 1,000? All right, so I'm going to go ahead and do this. The equation for angular momentum, there's two formulas we just saw, but one is L equals R times P. And we know in the past that R equals mass times velocity. So R would be, let's see, this distance. So the whole distance is 30,000 according to this. It says 30,000 kilometers. That means between here and here, it's 15,000 kilometers. And it already said that this distance here is 9,000. So the difference of 15,000, let's get this radius. So radius for this at position A is going to be 15,000 kilometers minus 9,000 kilometers, and so that would be 6,000 kilometers. All right, so in order to calculate the angular momentum, you take 6,000, and you want to get the meters. So you could say 6,000, add 3 zeros, so it would be 6.0. So I'm just going to put point times 10 to the 6th. That's changing kilometers to meters. Times the mass, that's 1,000. Times the velocity is 8,000. Multiply all those numbers. 4.8 times 10 to the 10th. And the units are, let's see, meters, it's like kilogram, meters squared, meters over seconds. Right, so that's the angular momentum. It has initially at point A, and then we want to find the velocity at point B. So we use conservation of angular momentum. So L at A equals L at B. We already got L at A, so we'll just write that down. 4.8 times 10 to the 13th. The angular momentum at B is RMV. We are trying to find the speed. So it'd be 4.8 times 10 to the 13th divided by Rm, that equals V. So then we just got to plug in what R and M are. R, in this case, we're talking the distance between the planet, the satellite. So the whole distance is 30,000, half the distance is 15,000. And then you'd add 9,000, so RB would be 15,000 kilometers plus 9,000 kilometers, which is 25,000 kilometers, which is equal to 2.5 times 10. This is 10 to the 4th, so that we add 3 zeros, 10 to the 7th meters. So when we do this math, it would be 2.5 times 10 to the 7th meters times the mass. Satellite has not changed, it's still the same satellite, so it's 1,000 kilograms. Get a velocity of 1,900 meters per second. So that's expected. We have increased the distance quite a bit. This was with 8,000, this was quite a bit further away. So the satellite should slow down, which it does. And that's also what planets do. They slow down the further they are away from the sun. Or more obvious is like comets. They come and sweep by the sun. They're going very quickly as they go past the sun, but as they get further and further away, they slow down because of conservation of angular momentum. All right, let's go to the next problem. All right, next problem, a disk with a mass m and a diameter of d is rotating at angular velocity omega. Two masses of mass m fall at opposite sides of the rotating disk. The masses are placed half the distance to the edge of the disk. Determine the rotational velocity of the new arrangement in terms of the variables listed. The equation for the moment of inertia of a disk is 1/2 mr squared, and our point mass is just mr squared. Okay, so the setup, we have this rotating disk. I'll try to draw this here as my disk. and these masses, we'll just have them above. The axis of rotation of the disk is right there, and it's spinning around here with omega velocity. So it's horizontally spinning. And these are going to fall halfway between these axes of rotation and the outer edge of the disk. So we're going to see their effect on the angular velocity of this larger disk. Larger disk is mass m. Smaller disk, or masses, are smaller m's. Alright, so we're going to use conservation of angular momentum. L I equals LF. And because the point of rotation is within the body, we will use the other formula for angular momentum, which is I omega. So I sub I initial, omega I equals I final times omega F. Just a side note here, the angular momentum vector is in the direction. So you cup your fingers around the disk, so the angular momentum vector would be in this direction, straight up. And it's part of the principle that a spinning object, it's hard to change its axes of rotation. So like something that's heavy or a wheel that's heavy, once it starts spinning, it wants to maintain that axis of rotation. And they use this principle to keep like the objects in the Hubble telescope from changing its direction, because if you keep this disk rotating like this, it will maintain its axis and it doesn't change its direction. Alright, well let's go ahead though and solve for I. This is just the disk itself, because these have not fallen on top of it. So the formula is right there, 1/2 mr squared. So I'm going to go 1/2. The mass was capital M, so I'm going to substitute that in. R squared. Let's see. They give us the diameter, so we know that diameter is twice the radius. So we're going to substitute in D over 2 squared. So if you do the math, you get D squared, so this would make this whole thing 1/8 md squared. Once these fall on top of the rotating disk, then the moment of inertia will change. So we'll call I sub F. This will still be 1/8. This is the same disk, so we'll call that md squared. We have two masses falling. We call those point masses. We use this formula right here. So it's 2 times. Alright, the distance, R, is the distance to this point of rotation. So if it falls right here, which according to the instructions, that's half distance from here, or 1/4 of the diameter. So I'm going to put D over 4, that's going to be squared. So let's have to simplify all this algebra here. 1/8 md squared, and you get D over 4 squared, that's D over 16, times 2 is 1/8. Oops, I forgot the mass. That's a little m. So 1/8 little m d squared. So that would be the new moment of inertia when these two masses are on here. And, okay. So now we're going to solve for omega f. So we're going to rearrange the conservation of angular momentum, omega I sub I, omega I, for I sub f equals this new angular velocity. We substitute in 1/8, this is over here, md squared. times omega. That's what they call this. It's right there. That's omega. Divided by I sub f. So it's going to be, factor out the 1/8 d squared big M plus little m. I'm factoring out the common terms, the 1/8 and d squared. That all equals omega f. Then we can do a little algebra. We can cancel 1/8. We can cancel d squared. And our final formula is capital M over quantity capital M plus little m, all multiplied by the initial angular velocity equals omega f. So that would be the new angular velocity, the rotational velocity of the disk after these masses fall on top. All right, thank you.